methods or natural language processing based methods, limitations of that. The new methods which are based on transformers that replace recurrent neural network or convolutional neural network, how they have transformed the way the input is looked at by neural networks and how classification or other tasks are done. We will be discussing today those specific mechanisms which help us understand better how we can relate different components of an input and can align them to have an improved performance of classification specifically, right? So my lecture today is on vision transformer, and vision transformers are based on attention mechanisms. And vision transformer, the core idea of vision transformer is taken from the transformers for natural language processing. And therefore, I will begin my discussion with attention mechanisms and then transformers and finally the vision transformer. So for the sake of improved quality of signal, I'm putting off my video and we will have discussion from time to time when I'll keep my video on. So let us look at these sequence to sequence tasks in AI. What are those tasks? What kind of tasks are those? Let us first look at speech signal processing. For example, the input is some speech signal, and the output could be an interpretation that comes out from here. For example, output can be in natural language processing in English, natural language, English, or let us look at machine translation, say from English to Hindi. It is again one sequence which is transformed to another sequence, or DNA sequence analysis, or let us look at the image captions, generating captions in videos. So a sequence of image frames are coming, video frames are coming, and you are generating captions. Okay, so how do we take care of, how do we make neural networks learn the sequence to sequence transformation tasks? So what happens that these sequence to sequence tasks expect the AI model to transform from an input sequence to an output sequence. So sequence to sequence models produce an output sequence of possibly different length m from an input sequence of length n. For example, if it is a simple classification task of the given feedback given by a participant in this course, and the classification task can be scored between 1 to 5, then the feedback has to be clustered in such a way that finally it classifies this, that's very good, good, average, not below average or poor. So it produces an output sequence of different, it transforms an output sequence of a different length possibly from an input sequence of a length n, say, for example. So in a typical recurrent neural network model that you studied yesterday, a recurrent neural network does what? It captures the information from the past inputs, say x0, x1, xt minus 1, and the current input to build its output sequence. That is what a recurrent neural network does. In some recurrent neural network models, the previous output is also considered. Like if you remember how a recurrent neural network works, you have an x0 and then x1, then x2, and each of these at these time steps, we call it time steps, although it is not always time step, it's a step. This information is processed and then probable output is generated, Y0, Y1, Y2, not necessarily at the same time step. And sometimes this Y0 is also fed to along with the next X0, and hidden states of these LSTM units or recurrent units are also shared with the next recurrent unit. So there are various types of sequence to sequence models that we have studied. Now here, let us consider machine translation task where, wow, it is so nice, is to be transformed to Hindi language. Now, so here you have a sequence of words and the current input XT is there to build its output sequence. So what happens that initially we start with a 0 vector or an initial word, start of a sequence word, and then we keep on translating it. And as I told you that in some cases, this is also, the output is also fed to the next LSTM unit for better approximation. You have bidirectional RNN also. In many applications, the output may depend upon the whole sequence of inputs. For example, let's consider this. The clip of her video telecast was amazing, and the clip on her hair was amazing. So the clip was with respect to hair, or clip was with respect to the telecast. Now this, sometimes this clip, to better understand interpret this word clip, it is important to have the future words in the sequence also. So in bidirectional RNN, the context present in the later part of the sequence sometimes attaches a different meaning to the word clip as in this case. So to address such issues, bidirectional RNNs were introduced in 1997, and they combine an RNN that moves forward the information and the processing and information processing in the backward direction. These are combined, and finally you interpret or take the probable word that is most appropriate for the kind of word or word that is most appropriate, probability of occurrence of a word. So output at each time step is computed using both past and future information. Now, why I am telling RNN, my dear friends, because RNN, the traditional RNN in the forward pass or backward bidirectional RNN, they are unable to deal with the long-term dependencies. Although bidirectional RNN significantly improved the performance of sequence-to-sequence model, long-term dependencies like I arrived at the bank after crossing the river. I arrived at the bank after crossing the road. This is the example I saw. These are two simple things. After crossing the road, after crossing the river. So the meaning of bank changes. I arrived at the bank after crossing the river or crossing the road. So it altogether changes the meaning of the word. So these are long-term dependencies that were not handled as effectively by normal RNN or even bidirectional RNN. Then came the concept of encoder-decoder architecture. What was the idea? The idea is, why not let us take the full input at a time and process this input, find out the hidden states or find out the interpretation or find out the representation of the input into a concise representation of the whole input, and let that input be further decoded. So that is the idea that was there in the mind of people who introduced the concept of encoder-decoder architecture. So this was introduced to deal with long-term dependencies and to address the challenges of variable length input and output sequences, because even in machine translation, you know that the input can be 5 words, output can be just 4 words, or input can be 3 words. I mean, there are many cases where the input and outputs will be of different length. So encoder in encoder-decoder architecture encodes the input sequence while the decoder produces the target sequence. So target sequence is what we expect. Target sequence can be Hindi translation of an English sentence, or French translation of an English sentence, or it can be an image captioning from an image from one single input of size, say 256 cross 256. I wish to have a caption. So the encoder processes the entire input sequence and produces a fixed length representation. Remember, what we do, that we are encoding the entire sentence into a fixed length representation, which is normally called context. The people who introduced the concept of encoder-decoder architecture for natural language processing, especially for machine translation, they use this concept they call it context. So context of the entire sentence. The decoder then works on producing the output for a given context representation, or the representation of the input. So encoder-decoder architecture, I mean, before producing any output, what happens? The hidden state at each time step. See, at each time step, like I arrived at the bank, I is a time step. Arrived, next time step. At third time step. So is computed. So what happens that this at each time step, the word I arrived, this goes to a LSTM units. Those LSTM units extract the features, and that is known as the hidden state of the encoder. So at each time step, I have this hidden state. That hidden state is also passed to the next time step for better interpretability of the input, better representation of the input. The output from the last hidden unit in the network serves as the global context vector summarizing the entire input sequence. Then the context vector is fed to the decoder network to produce the output. So this idea of encoder-decoder model works well for sequence-to-sequence tasks. So let us see how it looks. Let's take this wow. It is so nice. For the sake of convenience, I mean, I have removed the wow after comma after wow. Nice after nice also exclamation mark I should have removed. So suppose it is there. It goes to each word goes to an encoder unit, right? And the encoder units, each encoder unit will pass the information to the next encoder unit. It is passed to the next encoder unit, right? And so on and so forth. And not only that, after the last encoder, you have a final context representation, or the hidden representation of this entire sentence. This sentence can be, say, 25 words long or 5 words long. It can be any dimension, any length, but it is now encoded in a fixed length vector, right? Now, this goes to a decoder unit. Now, decoder unit will be starting with a, say here what happens, that start, we call it WSOS, means the start of the sequence, start of the sentence. So once that is fed along with the decoder, then the decoder will start taking out the words, the word at a one word at a time. This word is also fed to the next layer in the decoder unit, along with the hidden state of the decoder. And this keeps happening, and every time you get a new word until the end of the sentence is arrived. So although I have written here, "Wah, ye kitna acha hai" in Hindi, wow, how it is so nice translated, it may not always be as right as it is written here. It depends on the accuracy or the precision of the encoder-decoder architecture. So like if I look at the encoder, yes, these are, Krishna Chauhan is asking, is each of these is an RNN unit? That is what I have written. Like it can be an LSTM unit for machine translation. We use a LSTM unit. So suppose the problem is machine translation from English to Hindi. Each word from the input sequence is represented by a vector. Okay, X belonging to RD. D depends on the vocabulary size of the English language. So suppose I have 20,000 words in English language. Suppose most commonly used words are, say, 20,000. Now, what we do is that you must have seen in the lab sessions that these each word can be encoded to encoded to a one hot vector, or it can be further embedded. There are certain word embedding techniques. So it can be further embedded to put it in a lower dimensional space. So for the time being, suppose I assume that there are only 3 words in the vocabulary of our language, say X1, X2, X3, then these are encoded like 100, one hot vector, the first word. The second word will be 010, second word, and the third word will be 001. So in this way, one hot encoding exists even for machine translation or natural language processing like jobs. And then so this will become a 20,000 long vector of size 20,000, which can be a very long vector. Therefore, what people have done, that they have found, in natural language processing, people have found out wonderful word embedding methods which transform words to lower dimensional spaces. That is, some kind of projection methods are used. So suppose input sequence is wow, it is so nice. For the sake of convenience, let us remove the punctuations. So the word sequence is wow, one first word, it is so nice. 5-word input sequence belonging to R to the power D, that is D-dimensional words, these are. Then we run an LSTM model on these 5 inputs. We get 5 hidden states, E0, E1, E2, E3, E4, and each previous hidden state is input to the next encoder unit along with the next input in the sequence of inputs. And the output from the last unit, say E, is supplied as the context representation vector to the decoder, and the hidden representation of the input, or simply the input representation. Now, so vector E is assumed to have captured the meaning of the input sequence. So we are assuming that the large sentence is, very long sentence is captured, its meaning is captured in a fixed length vector. It is used to generate the target sequence of words. So then it is fed to the decoder unit as a hidden state with a starting probable word in Hindi, say WSOS, start of the sequence word. The next hidden state H0, I seek your attention, please. The next hidden state H0 belonging to RH. Now, Hindi will have a different vocabulary size. So H0 belonging to RH is computed using E and WSOS. So the next hidden state will be found out. Next, H0 is transformed to another vector, S0, belonging to RV, a vector of to match the size of the some people are asking some question. I will answer those questions. Please wait for a while. Let me first explain. H0, so you get a hidden state. You know that convolutional neural network or recurrent neural network, the size of the output will depend upon what is the structure of your neural network. Depending on the structure and the last number of units in the structure, the hidden state will have a different dimension. So here the different dimension you have RH. What we are doing to match it with the vocabulary in Hindi, we are transforming it to another vector S0 to match the size of the vocabulary in Hindi. So suppose in English there were 20,000 words and in Hindi there are 32,000 words. So this has to be mapped to another, it has to be lifted to a higher dimensional space. So naturally you will be applying a matrix transformation. So finally we apply softmax to S0 to find out the vector of probabilities in RV. The corresponding word with highest probability is chosen to be the first output word WI0 in the output sequence. I hope this is clear to you. Now let me come to the question. How we decide about, so Deepthi is asking how we decide input sequence in multiple output means in multiple language. I just don't understand what is the question. I'm sorry, I don't understand your question, but it seems that you are talking about multilingual. Then you will have to combine the most common frequently asked, frequently occurring words, and you will have to create your own vocabulary of multilingual language, multilingual inputs. Accordingly, you can have a vector dimension space, vector space of that dimension, and you can apply word embedding theorem and algorithm, and then you can create your vocabulary, right? Have I answered your question, Deepthi? Thank you. So what happens that, let me explain what happens. So in this way, WIT is the output word at tth time step. So I seek your attention here. Equations for this. H0 is LSTM applied on WSOS, the starter of the word, and the hidden state coming from the encoder. S0 is some operation on H0 that will be transforming an H dimension vector, H dimension to V dimension, right? V dimension. Okay. And then P0 is the softmax on S0. Now this is V dimension vector. Now let me write here V dimension vector. So suppose V is say 10, right? V is suppose 10. So I will be getting a vector because I have applied softmax operation on S0. So I will be getting say 0.1, 0.0, 0.2, 0.1, and so on and so forth, and say 0.6, 0.1, and so on and so forth, right? So this is the one, like if I look at this at 9th position, for example, if V is 10, at 9th position, I'm getting the highest value. So next, what we do is that I0 is the arg max of P0. That means the argument That is maximizing the probability of occurrence of a word. So if V is equal to 10, the first word if suppose your vocabulary contains 10 words, say first word is say V, the second word is say R, the third word is going, and so on and so forth. And this ninth word is market, right? Suppose. So this corresponding probability, that ninth position, it gives me the highest probability of occurrence of this word. Accordingly, I0, once the I0 is obtained, you are able to find out what is the corresponding word. This is how the recurrent neural network works. Right? So this is what is happening in the at the decoder level. So the current output is fed to the next decoder unit as the input. HT is equal to LSTM, HT minus 1, WIT minus 1. And ST is equal to GST, PT is equal to softmax. So this process continues. And every time we find out the maximum argument that is maximizing the probability of the occurrence of a word, and corresponding word is chosen, right? So the model aims at finding out the most probable next word by maximizing the probability that given WT minus 1, W0 and hidden state E of the last encoder unit, what is the probability that the next word is DT plus 1? What is the probability that the next word is WT plus 1? And since this E depends on the input sequence, so basically we are looking at the probability of the next word, WT plus 1, given that the previous words have occurred like WT minus 1, and all the previous, the entire sequence of words in the encoder unit. I hope this is clear to everybody. Is this clear to you? How encoder-decoder architecture works? Please say yes if you have understood. Thank you. Thank you, Nanshri. Thank you, Deepti. I think many of you are able to understand. Thank you. Thank you, Samir. Well, so, okay, when this encoder-decoder architecture was there, why attention was required? What is attention mechanism? What happens if the size of the context representation vector is too small as compared to the input sequence, right? Like the bear could not cross the road because it was too tired. The bear could not cross the road because it was too wide. This is an example that these people who introduced the concept of transformer gave. Like the bear could not cross the road because it was too wide. The bear could not cross the road because it was too tired. So it was, where is what is the attention here? Like it was tired, right? Sorry. Let me write. It was tired. It was wide. What was it? In the first case, it was the bear. In the second case, the road was it. It was road. So something which is important here to learn is the what attention we need to pay while processing the word. Now you must be thinking that we have already discussed it while creating LSTM. LSTM, my dear friends, is, thank you so much, all of you who said that you have understood. Now, LSTM, what does it do? LSTM also looks at the long-term dependencies and keeps forgetting those words whose context is now no longer required, and words or the features whose context is still required. They will keep on carrying on this. However, LSTM did solve to a great extent the vanishing gradient problem. It was unable to deal with long-term dependencies for many cases. I would not say that LSTM failed to address the long-term dependencies. At the time when we had less number of data, with 1,000 units, 1,000 depth, LSTM depth, it was, I mean, people were able to successfully do the natural language processing, even in the 90s, in the decade of 90s. But there were many things which were not properly handled. For example, just Deepti asked, what about multilingual inputs? There are many things, many new challenges that were posed before the language processing AI models. So then came the context of this attention mechanism. How is the context of each input captured in a fixed length context representation vector, right? So Bahadaniu introduced, it's not very old model, introduced a variable length context representation for the input with the concept of attention mechanism. Attention mechanism retains and utilizes all the hidden states of the input sequence during the decoding process. Remember that each hidden state coming from different encoder units is being retained and it is being utilized, right, during the decoding process. Let's see how. So attention-based encoder-decoder are based on the attention-based models are also dependent. This attention mechanism, is based on encoder-decoder architecture only. The encoder encodes the input sequence, right, while the decoder produces the target sequence, like the one we have done. Now I seek your attention, please, to see how it is treating the input. Wow, it is so nice. Encoder units. Now each encoder unit will be producing a hidden state, as you can see here, this hidden state. Hidden state is producing, and that is also being captured by the context vector, right? As you can see here, the last, from the first to the last. Then this context vector enriched with the individual hidden information with certain weightage given to each individual hidden state passes the information to the decoder unit. And then decoder unit not only uses the context, only the first decoder unit uses the context vector along with the hidden information of each individual unit of the encoder, but also each individual decoder layer will be dealing with this context vector along with the hidden states of all the encoder units, giving weightage to each encoder unit. So as you can see that it is also passing the information to the decoder unit, the first word that comes out along with the context vector, and the information is passed to all the decoder units. This is the basic difference. So naturally, this was for some improvement. So the idea was pay attention to specific parts of the input sequence. Not all the input is important. Like, for example, if I say that there was an earthquake in the Hind Kush area yesterday, right? So earthquake is important. Where is important? There was is not so important, right? Right. So there are certain points which are not, there are certain words which are not so important. There are certain words which have some kind of relationship with other words. Like if I say earthquake, where? Hind Kush area. When? Yesterday. These are two important connections that we have to understand. And we expect our natural language processing model to learn this interaction, learn this alignment with the other words. So at each time step, a context vector is also added. So change in the equation, right, is as follows. So the next hidden state coming out will depend on which LSTM will process it, and it will be based on, say, the previous hidden state from the decoder, the current word, and a context vector. This context vector is, let's see what is this context vector. So exactly the same way as the previous encoder decoder unit, except that a context vector is added here. And then we transform it to a different dimension, project it to a different dimension, apply softmax operation as we did before, and then we find out the vector of probabilities, and we take out the argument, the label with the highest probability, and that is the word that is the probable word that we find out, right? So the question is, what is this context vector? So how is this context vector computed? Remember that at each time step, we are, in the previous case, we used to have ht minus 1 and the hidden state of the context representation of the coming from the entire encoder unit. But now here it is, say, EJ. What is EJ? EJ is the hidden state coming out from the jth unit of the encoder. So at each time step t, compute the score of the hidden state EJ for ht using a function f ht minus 1 EJ is equal to alpha tj, right? So this hidden state is from decoder. It is corresponding to the hidden state from jth unit of encoder. The softmax operation function is then applied on the sequence alpha t, which is equal to alpha t0, alpha t1, alpha tn. Suppose there are n units in the encoder sequence, right? What I am doing? I am finding out a function which relates the hidden state of the previous decoder unit with the hidden states of all the n encoder units. Equation for computing CT are as this: alpha tj is equal to ft minus 1 ej. Then what I do, I apply softmax operation and this entire vector, each component, we apply softmax operation. That means I take the sigmoid function is applied on this. Then alpha t bar is computed like it is a softmax alpha t, and then using this alpha t bar, I'm defining CT. So what is CT? It is a weighted average. It's a because this softmax will make it between 0 and 1 with summing up to 1. So it's a weighted average of hidden units states from the encoder. How much weight I attach to the EI unit, to the ith unit EI, corresponding to the previous hidden state of the decoder unit. Accordingly, this context vector is presented to the current hidden unit of the decoder unit. Is that clear to you all? Please say yes or no if things are not clear. Is this clear to you all? Thank you. Leela Darji, thank you, Nayan. Thanks, Gayatri. So if there's anybody who is not clear about it, please, why softmax function is used, not ReLU? What bar represents? See, ReLU is what? ReLU is only done what for? ReLU is a function which is suppressing the negative information. What do we want? We want to create weightage for each EI. If I use a ReLU operation, then what will happen? Now here, I have to look at the, so this, what is this? Basically, this is giving me that if this value is a little higher, I have to keep it between, I just want to keep it between 0 and 1 so that things do not go out of proportion, number one. Because here, if the values are high, this will give me a high value. And that is the reason, if you remember, we also normalize the, hello? We also normalize the inputs. If you remember, any given input is also normalized, right? So here, alpha Ti is telling me the weight. So alpha T bar is what? Simply apply softmax operation on this alpha T vector, I will be getting alpha T bar. So once I apply softmax function, you know that this is a m-dimensional extension of sigmoid function. And sigmoid function is what? It is, its values lie between 0 and 1, right? That is the purpose. So higher is the value of alpha Ti, higher is the probability that EI needs to, the decoder needs to pay attention to the word EI or to the hidden state EI, right? And the corresponding word, right? So when I say that I arrived at the bank after crossing the road, I arrived at the bank after crossing the river. So this river or road, right? So all these things depend upon, like, bank, how should I treat bank in my later sentences will be governed by how do I interpret these two sentences. So attention score, so I used a function FHT minus 1 EJ, FT minus 1 H. Got it. Thank you. Thank you. So I used a function here, which is based on two inputs, two arguments, HT minus 1 EJ, and it produces some value alpha TJ. Now, what will be the choice of the function? What choice of function? That choice of function is known as attention score. So choice of the function FHT minus 1 EJ can be general dot product attention. Like I simply take the dot product. Here I'm assuming that the same, both of them. Some of you have unmuted your mic. Who is the person who has unmuted his mic? May I request you to please either mute your mic, or if you have any question, please ask that. Thank you. Thank you. First very simple choice can be, we just take a general dot product attention. We take the dot product. So why dot product? Dot product because it is easy to calculate, number one. Number two, sometimes people also use scale dot product attention. Scale dot product attention is used by Vaswani when he defines transformer network. So scale dot product attention can be, for example, this, where D is the dimension of the vector, right? Some people have also used weight metrics for learning to pay attention. Like here, all the transformer that we are using now, they have used this kind of attention. So they first take a weight parameter, and then they apply weight parameter on EJ, weight parameter matrix, and then they take the HT-1 transform and then take the dot product. So it is also a kind of dot product attention, but here is a learned attention. It's a learned attention mechanism score that we will be using. So recall that if two vectors are aligned, their dot product gives a high value. If you have two vectors here, this is one vector, this is another vector, this is the angle theta, and you know that the dot product of these two vectors is basically mod A mod B cos theta, assuming that theta is positive. So let's say that let's consider theta is between 0 and 90 degree. So you know that the cos of the angle will be higher if theta is smaller, right? So, sorry, theta is small, then cos of the angle is higher. So that means this, if the two vectors are aligned, therefore, if they are aligned in the same direction, then one can say that they have some kind of, one can interpret that they have some kind of relationship, and therefore the attention score should be higher, right? Why people have taken this scaled dot product? Because for very large vectors, sometimes the dot product attentions give very large values, and therefore people have realized that this can lead to some kind of divergence from the sequence, and people have applied scale dot product attention. So let us look at the attention mechanism. Think of the hidden state HT-1 of the decoder as a query to find alignment with the hidden states of the encoder at different time steps. Okay? Let us look at the encoder states. So you have these encoder states which are available with me, say E0, E1, E2, and so on and so forth. So what I'm doing is, with respect to the previous hidden state of the decoder, I'm trying to find out how aligned this decoded state is with respect to the hidden state of this word, hidden state of this word, and so on and so forth. So treat these hidden states EJ at time step Tj as the keys that reveal the values, the relevance with respect to the query, right? So what I'm doing is that I have got a set of encoded states of different words, and I have got the decoder at time step T, which is trying to interpret what should be the word for the current, what should be the current output. For looking at the current output, it will look at its previous hidden state, and it will also try to align the previous hidden state that it has taken out with the encoder states of different words in the encoding stage. And then it will create a score. So that is what we are doing, right? So what we have different keys. Responding to those different keys, we have values. So for example, let us think. The keys can be, say, let's look at the database example. From the database, you have a key value pair. The key can be any key that you can use, say, for example, the age, the state from which you belong, or all those these could be different keys corresponding to which there can be various values, and those values are associated based on the key. So for example, if you are a participant from, say, India, I will be giving different weightage to a participant from India, maybe from Pakistan, different weightage. Why different weightage? Because these programs were basically primarily are introduced for India, Nepal, Bhutan, and Bangladesh. But if there is somebody from Pakistan or Sri Lanka, or for that matter, any other country, we pay attention. That means there is somebody from not in this, not from the jurisdiction of this, but he has or she has shown interest. So we will be paying attention to people covered in this from this country and people who are not from that country, right? So what I intend to say is that it is just like a key value pair. So corresponding to the key, what is the value that will come out? So that is what is attention score function tells. So we find out the dot product, for example, and these values will be created. Then we apply softmax operation. Then we attach a weight and the values are created. Corresponding to those values are created. Okay, I hope this is clear to you. That attention mechanism basically looks at queries for all the aligned words from the input domain and attaches and associates an alignment score that serves as a value for giving weightage at the decoder stage. So now, yes, these key values are different attributes. For every key, we have a different attribute. For every key, we have a different attribute. Like if this, for example, if it is, then the value should be low. If it is, say, I said that yesterday, earthquake hit Hind Kush area, right? So Hind Kush, yesterday, and earthquake are very relevant. So for them, the values will be high. And for other words, the values will be low. So that is the key value pair. I say that the key words like is, then, here, there, the values will be low, right? And if I say we are fetching the information about the earthquakes and we are looking for Google search, the Google will pay more attention to earthquake and where and when, right? So that is what is key value pair. Okay, thank you. So now when we talk of attention, there are various kinds of attention. I wanted to cover different types of attention, and one of the attention mechanism my student has discovered for vision-based task, Samir, who is attending this course. So Samir has come out with a wonderful attention mechanism, but the time does not permit us to go ahead with the other attention mechanism. Let me first talk about the self-attention. The attention mechanisms can be between the input and output elements, as discussed previously, or it can be within the input elements. That is self-attention. Like, what do we mean by self-attention? Like, I mean, if I look at the sentence that there was an earthquake in Hind Kush area yesterday. So here itself, the meaning of earthquake, the moment I say earthquake, then when and where are automatically connected. So that is where we can say self-attention. So self-attention is also known as intra-attention. is an attention mechanism that relates different positions of a single sequence to find out a representation of the sequence, right? As I told you that what value should I associate? What value should I give to represent this entire information? This information is on earthquake, this information is on when and where, right? So basically, the self-attention helps us find out a better representation of the input data, a finer representation of the input data. So here comes the transformer network. The transformer, this was introduced by Ashish Vaswani and his friends, his colleagues from Google Brain and Google Research in their celebrated paper, Attention is All You Need, that appeared in 2017. The transformer follows the overall encoder-decoder architecture using stacked self-attention and point-wise fully connected layers for both encoder and decoder. Remember that there's no recurrent neural unit, there is no convolutional unit, only fully connected layers for both encoder and decoder. It relies, so it's an altogether different network, my dear participants, because this network is created taking the benefits from the experience in the past of recurrent neural networks and on convolutional neural network. So it relies entirely on attention mechanism to draw global dependencies between input and output. That is very important, that it draws global dependencies between input and output. Let's see how. This is the structure of a architecture of a high-level architecture of a transformer network. A single layer, right? Yes, and there can be n such layers. You can see these n such layers can be there. N into this, oh sorry, n layers here and n layers here. So this is the encoder and decoder architecture. So input embedding and output embedding. It is encoder and decoder architecture. So encoder contains a stack of n identical layers. This n in the paper by Ashish Vaswani is taken to be six identical layers. Each layer has two sublayers. The first is a multi-head self-attention. Don't worry if you don't want to know what is a multi-head self-attention, I'll explain you. The second is a simple position-wise, fully connected feed-forward network. Position-wise, fully connected feed-forward network is like a 1x1 convolution that you will apply on each input to on each output coming from here, right? It's a residual connection, as you can see, around each of the two sublayers. Professor Khanna has covered what is a residual network. So it's a residual connection around each of the two sublayers, followed by layer normalization. That is also added here. And after all sublayers, like all sublayers in the model, as well as the embedding layers, produce outputs of the single dimension D, right? So it's called D model or whatever dimension you could call it. So let us clearly see what it is doing. First of all, the input embedding, right? This, as I told you, that embedding can be any kind of embedding that you would like to apply on your input sequence. That embedding can be a word embedding, right? Then we do positional encoding. What is meant by this? Like, where is this word and how this word positions itself in the sequence, right? That is what is positional encoding. So I am having, otherwise without positional encoding, it will be just a bag of words. So positional encoding fixes its, I mean, you can say that fixes its position with respect to sentence, right? So if it is a sentence, because we are talking about transformer, natural language processing transformer, so it will be like this. So all sublayers in the model as well as the embedding layers produce outputs of dimension n. So first of all, let us look at what is attention here. So this multi-head attention is basically a self-attention mechanism, multiple self-attention mechanism, multiple self-attention. These are there. And then what is this add and normalization? So basically it is an adding and normalization being done. Let me tell you what is done. So suppose from here, after the multi-head attention, if suppose the inputs are coming, say from multi-head attention, I concatenate all of them, x1, x2, x3, x6, say, suppose these attentions are coming. And then we have to add the input that is coming from here to this. So what I will do, like, let this be x. So I will be adding, say, let it be called x prime. So I will be adding x prime to the initial x that is coming from here, initial x that is coming from here, x. And then I will be applying layer normalization. What is meant by layer normalization? By layer normalization, I mean feature-wise, I will be doing normalization, right? If you have a batch, right? If you have a batch of 3 vectors, in a batch of 3 vectors, I will be considering the first feature of every vector, the second feature of every vector, the third feature of every vector, and so on and so forth. And feature-wise, I will be doing the finding out the mean and standard deviation and will be normalizing each vector. That is what is layer normalization. Is that clear to you? Please say yes if you are clear about it. Okay, thank you. And then we forward it to point-wise fully connected network, point-wise fully connected feed-forward network. Then we pass it to this so that each point is treated separately. Then we again apply add and normalization. And then this encoder unit, like these are n number of such layers, then these layer output is fed to the decoder part. Like, how do we do? Now, so let me go ahead with the encoder and decoder part. In the decoder, let me first complete the decoder part. And thanks to all of you who said yes. The decoder also contains n identical layers. In addition to the 2 sublayers in the encoder, the decoder uses a third sublayer to perform multi-head attention over the output of the encoder stack, right? The self-attention sublayer in the decoder stack is modified to prevent positions from attending to subsequent positions. This masking ensures that the predictions for position I can depend only on the known output at the position less than I. I see what it does. See, here I'm getting the encoder's output, hidden states. What this is doing? From here, basically, if you start from the start of the sentence word, then this is masked here. Why? Because there is no previous word that is already generated. But for once the first word is generated, the hidden state from the first unit is this unit is on. that the second word that is generated, the first word is generated, the second word would like to have information about the first word, right? Because these are all parallel going. One thing which is very important for transformer networks, that the recurrent neural network were actually working in a sequential way. So it was not possible to parallelize the coding, implementation of that. If you wanted to parallelize, it was not possible. So here what we are doing, we are separately dealing all the stack and those n units, and we are sending it to the decoder unit also simultaneously. And decoder unit must be refrained from looking at the future words. It has to only depend on past words generated so that it can precisely generate the current word. And that is the reason this masked multi-head attention is used. So this masking is especially for hidden states coming from the previous part of the unit. So an attention function is a mapping of, so what is attention? Basically, it's a mapping of query Q and a set of key value pair in an output. Here Q, K, V are all vectors. The output is a weighted sum of values where the weight assigned to each value is computed by attention score of the query with the corresponding key, as we did in the previous case also, if you remember. So that is why I started with the encoder-decoder architecture. So attention Q, K, V. What is Q? The current hidden, the hidden unit, the hidden state that is coming from the previous decoder unit. K is the all possible keys present in the encoder unit. Value is the value that we associate to this, right? So attention Q, K, V basically is looking like this. Q, K transpose under root dk and v, right? Now here the dimension of qk is dk, and the dimension and qkv are nothing but matrices containing the set of qkv. So what we do, as I told you, that we do parallelly the computation because there are n multi-head attention. So all the attentions are parallelly computing the things. So instead of just one query, we will be stacking all the, say, k queries together, right? So this becomes a matrix of k queries. Corresponding, you have, say, keys, certain keys, and we take queries and keys of the same dimension, and then we can be in another direction, the value, right? So multi-head attention, QKV, multi-head will be concatenating the values coming from the outputs coming from different heads, and then applying a learnable matrix to pay attention to different units and different heads. Attention, this head QKV is what? It is basically the attention of QWQ, KWK, VWV. Here, each of these are learnable projection parameter matrices. All of them are learnable projection matrices. Why projection matrices? Because you know that we are transforming from one dimension, one space to another space. So one need to project from one dimension to another dimension. So there are learnable projection matrix. And if you see, there are three uses of attention, multi-head attention. The encoder contains self-attention layers. In self-attention layer, all of the key values and queries come from the same place. In this case, the output of the previous layer in the encoder. Remember that in the encoder layer, we are using self-attention. So what do they do in the encoder layer? They are looking at the self-attention from the input space only, right? They're looking at the self-attention of different, the alignment of different words in the sentence, right? So input, in this case, the output of the previous layer is in the encoder. Each position in the encoder, are you getting my point? That you have these words, each word will be looking at its like what is its context with respect to the word which has previously occurred, or the word which is going to occur in a later time step. So encoder contains self-attention layer. So here the query, for example, for this, the query can be this word, and the keys can be this word, and this word, and this word. The all can be keys, right? And the value will be associated with respect to their alignment with respect to with these words, right? Is that clear to you? That alignment, if this, suppose this word, the second word is having higher alignment with the fourth word, the value will be high. If the second word is having lower alignment with the fifth word, the value will be low. That is what is key value pair. So in the decoder layer, so one is in the decoder layer, the queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder, and this allows every position in the decoder to attend to all. So basically, we are using self-attention in the encoder to find out the key values. In the decoder layer, it is also looking at the queries from the encoder layer, and the self-attention layer in the decoder allows each position in the decoder to attend to previous position and including up to that position, right? So basically, if I do this attention blocks, you can see that scale dot product reduction, you do a mat multiplication, then scale, then you can mask. In case of decoder, you put a mask. In case of encoder, no mask is needed. And then we apply multi-head attention, a stack of, say, various self-attention mechanism, concatenate, and then you apply a linear layer. This is how it is done. And I would like to run this for you, encoding and decoding process. You can see that in encoding, multi-head encoding, it is done. And at each layer, this I got from TensorFlow blog. And you can see that the first word, the second word that is there, and the third word that is created. So basically, it is taking attention from the previous layer and all the encoder units, right? That is what is happening. So what are the benefits? They can significantly perform better in modeling sequential data. Unlike RNNs, transformers use attention, and therefore parallel processing of data is possible. Transformers are designed to capture distant or long-range context and dependencies. And transformers make no assumptions about the temporal or spatial relationship across the data, unlike the sequence-to-sequence models previously used like RNN or CNN. Now, I come to vision transformer. Basically, this is purely inspired by transformer success in natural language processing. And in vision transformer, what we do is that an image is split into fixed size patches, and each patch is then linearly embedded, and one-dimensional positional embedding is added. The resulting sequence of vector is fed to the standard transformer encoder. For classification, an extra learnable classification token is added to the sequence. Let me tell you, how does it do? This is also from the GitHub code, GitHub. You can see that how it is working, And because it is only requiring, because vision transformer here is for classification task. So first of all, these patches are flattened, right? And linearly projected. Now this linear projection is again learnable linear projection. right? It can be just a simply flattening, or it can be learnable linear projection of flattened patches. So first we flatten the patch. If it is a 2 cross 2, we make it 4 cross 1. And then we apply a linear projection. Then each patch is having a positional embedding. Now, this positional embedding is not very, very straightforward. For example, this can be 1, 2, 3, 4, 5, 6. So this position is there. Not exactly like this. This positional embedding is basically based on its relevance in the entire image, right? How relevant this is with respect to the image information that I have. That is what is positional embedding. Plus, there is a class embedding. What happens that the initial layer, this initial, in the stack, the initial, you have an initial layer that contains the class information. What class this image belongs to for vision transformers. Okay. And then this goes to exactly the same way as in encoder of the vision of the transformer unit. So it is just simply the encoder of the transformer, and then we don't need decoder because we are doing the classification task. So then it is the encoder basically fetches the information and extracts the features from the images, which is then sent to multi-head attention, MLP heads, and then finally the classification is done. So basically a linear projection layer, I'm sorry, I'm going a little late, but it's only 7:25 right now, but I think I'll be able to cover a linear projection layer that maps the input patches to a feature vector that the flattened patches into, that flattens the patches into a lower dimension space. Remember that if you have a 224 cross 224 image, and if you choose, suppose, a patch of 2 cross 2, it will be a very large size vector that will be produced, flattened vector, 2 cross 2, 2 cross 2, there will be large feature vector that will be produced. So you have to lower the dimension of the space. So generally the linear projection layer can be, you take any learnable learnable matrix transformation that can lower the dimension of the feature vector. The linear layer takes each patch independently as input, this linear projection layer, and it downsizes the input. A classification token is added to the input sequence, remember? The output feature vector of the classification token is used for classification prediction. So you have a classification token that is also added to the input sequence, as I showed here. Here, this classification token is there, right? Okay. And then you have a learnable positional embedding are added to the tokens before being processed by the transformer. In the natural language processing, here, there was no learnable the positional embedding was not learnable. It was a purely based on the sign of the base. You can say the dot, you can consider the dot product, and you consider the how can we say, the similarity was found out, some kind of alignment was found out using a sinusoidal transformation. So here it is learnable position embedding that is used, and LP are needed to learn position dependent information and convert the image information to a sequence data. That means how different patches are aligned to represent a pattern, right? MLP head is added to take the output feature vector of the class token and maps it to a classification prediction. So MLP is a small feed forward network, or one can even have a single linear layer. That is what is done in this. Vision transformer for segmentation is also available, where what we do in brief, I will tell you that after the encoder, transformer encoder, the mask transformer is another encoder. So that takes basically from each patch, the features of each patch are mapped to a classification of the, in the segmentation. For example, this can be, these pixels can be classified as having buildings, right? So basically, this is another encoder that is used, that is applied on the output of the transformer encoder. And then this is mapped with these classification score or the classification token, and pixel-wise classification is performed, right? So then these flattened patches are again, they are mapped to a two-dimensional array, and each array is then transformed to areas which are based on the pixels, which are, we can say that, or belonging to the class tree or sidewalk or person or something like that. That is all from my side. It is exactly 7:30. If you have any questions, you can ask. Else, thank you so very much for your participation in this session. And vision transformers have made significant advancements in practically all vision-based tasks. So what is global context? Because this context that we are looking at, it is globally searching for basically what it is doing. Every single positional embedding that we do is globally searching for patterns similar to the pattern that is existing in one part of the image. So basically, we are looking at the global context of the image, right? And global context of the image can be, for example, the image is containing a human face, or the image is containing a tree, image is containing some walking person. So that can be obtained by looking at how different parts, different patches of the images are aligning each other in creating a specific information. So for example, in one part of the image, suppose you have a hand, like you have a hand information, or suppose this is the hand. Let me make it better. So suppose this is a hand information, right? So you have hand, right? So this is hand information. Some part of the image contains part of the hand. Another part of the image contains another part of the hand. And the third part contains. So when we take the information, when we find out the positional encoding, and then find out the context, global context with respect to the positional encoding, the feature vectors which will be coming from this part of the image and from this part of the image. So this is the query, this is the key that is coming here. And if these queries and keys are aligned in some way in terms of the texture, the color of the hand, then the value that is to be associated in identifying that this image contains a hand will be high. That is how these are learned. So this query and key make a learnable system that identifies or associates a value to be given in the context of image classification containing hand. I hope this is clear to you. Is this clear? Okay, thank you. Any other question you have? So if there are no questions, I would like to stop share and take your leave. Thank you so very much, all of you, for attending